So today we're going to talk about something that actually I do get asked about a lot, and that is traps in general. We're mostly going to focus on obviously the oil side, but there's some other topics in there as well. But I guess just to get started, because obviously you're from market refrigeration is what you work in day out grocery store
That's right.
stuff.
Yeah, absolutely.
So you have a lot of experience with traps, and as we talk about this, I'm going to try to, to some degree, interpret it for an HVAC audience. But it's good. It's good information and kind of applies either way. But yeah, from your perspective, where are maybe some of those differences?
Yeah. So, refrigerant's the same, oil's the same. It's got to get back to the compressor. It's going to flow through the suction lines. We're going to have velocity changes. We're going to make elevation changes, stuff like that. That part is all the same. There's really not much difference there. When it comes to market, the reason why we deal with traps so much is just the length of the runs and the height that we're typically moving that refrigerant. It can be, 20, 30 feet, and it's not one system, it's 82, so you really have got to nail it. And if you get it wrong and you have a problem, there's so much oil in the system that you'll be 13, 14 gallons into a mistake before you figure out, where that oil is. And when you find it, it's all coming back at the same time. So you're getting 13, 14 gallons back. You're going to break compressors, right? So it's more critical in the supermarket world. It's more of an extreme example of using traps in the supermarket world, but it applies to any time, we're putting a condenser over the evaporator type setup, or even the pipe goes up and then comes back down, those type of environments, or it goes down and then comes back up. Anywhere we can create an unintentional trap, it's probably worse outside of the supermarket world. That's probably a bigger problem. Not recognizing I've made a trap and it's big. On a remote condenser setup, for instance, that's kind of a common problem when guys set a condenser on a roof, and we've got a walk-in box downstairs, and I'm running that pipe from that evaporator all the way up to the roof, and then I've got to bring it into a condenser. I may not be thinking I'm creating traps, and my oil is going to get stuck in between these two places. Or when I shut off my compressor, my condenser now is higher than my compressor. It's going to drain into my compressor, right? So those are some of the challenges that just not being aware of what's going on can create.
Yeah, so from a very basic standpoint, if somebody's like traps, I know about that. It's where you take your drain line and it's okay. We're talking about refrigerant traps here,
Right.
And we're literally just saying anywhere that it goes down and then back up, at least the diameter of the pipe, I guess.
That's
technically is a
exactly,
trap at
that's
that point.
exactly right. If we cross the diameter of that pipe with a vertical climb, and like you said, we're coming down and then going back up, that line is going to fill up with oil on the suction side, right? On the suction side where I have vapor. My vapor has to bring that oil back to my compressor. It's going to do that through velocity. And anytime I have a loss in velocity and gravity is involved, or the system shuts off, if we cycle it, for instance, that oil is going to fall to the low spot. That's where it's going to go. Well, that's going to be this thing we've created unintentionally or intentionally. That's where it's going to fall to. So we want to collect it there on purpose, and we want to do it in the proper way so that it clears itself. That trap brings that oil back in a manageable amount. That's liquid, right? We can't feed a compressor with liquid. It'll break. So we've got to bring it back in small little sips rather than giant gulps. That's the concept. And if we build one unintentionally, we'll run out of oil on a small system, a single compressor type setup. We'll lock out the compressor. It'll run out of oil. So we'll add oil, and we'll keep adding oil. And then when that trap finally gets full enough to clear, we get all that oil back at one time. That's when we destroy things. Right?
Yeah. Sips versus gulps. That's something that we talked about in a past podcast, and that's kind of stuck with me, a good way of thinking about that. You gave a good example when we were kind of prepping for this and talking about it, where you, again, working in markets all day, every day, big rack systems, you always have to think about this. But we did a job where some of our commercial HVAC guys did a small job and weren't really thinking about it. And just talk quickly about kind of what happened and the consequences there.
Sure, yeah. And I see this a lot. When I walk rooftops in the commercial world, I see condensers. I'm just naturally drawn to them. It may have nothing to do with why I'm on that roof, but I got to look, right? So I do see this quite a bit, and it's just not being aware, right? If I've got my evaporator, in this scenario, we're talking about my evaporator's downstairs. It's hung in the ceiling of a walk-in, but it's below the roof line, right? And then I set my condenser on the roof line. Well, that pipe is going to go through a gooseneck. It has to penetrate the roof in a weatherproof manner, right? So we typically come out of that gooseneck, and then what we typically do is just kind of U back down to the roof deck and strap our pipe along the roof deck to the condenser, right? Well, guess what? If I'm then going up to my condenser, oh yeah, giant U, right? We've just created a huge U. What is that? Well, U is a trap. Right. And the farther that run is, the more oil that is going to hold in that suction pipe, right? So, so the simple fix to that, the problem we had, by the way, was exactly what I just described. We were locking out on oil. Now, with some of the supermarket guys got involved and they knew better than to add oil. If you run out of oil, it's somewhere, find it. So they didn't add oil. It didn't cost us that compressor. And we just added an intentional trap right at that, quote, riser at the condenser where that pipe leaves the roof deck and goes up to the condenser. We added an intentional trap there. Well, now we're emptying that giant trap through those little sips in our intentional trap. Problem solved. Went away. So that's just an example of a single compressor system, with a walk-in type setup, super common. Remote condenser on the roof, and just not paying attention to coming out of that gooseneck and then the elevation of that pipe when it hits the compressor.
Yeah, and again, Copeland's the one sponsoring this particular video, and they're interested in not having their compressors fail, which you talked about. Obviously, if you run out of oil and you don't have any controls, that's bad, right?
That's bad.
Assuming you have oil controls, then it's going to shut the system off. But to your point, if you have enough oil in the system that then it comes back all at once, having too much is just as bad as having too little. So talk about that a little bit. Why is having too much oil a problem for the compressor?
Right. Yeah. So the first one is that oil safety shutting off the compressor. Let's talk about that for a second. So, Copeland's controls these days are really precise and really fast. But it still doesn't matter. You have to run out. The event has to happen first. You have to run out of oil before it turns it off, even if it's just seconds or a millisecond, right? So running a mechanical device with no oil for any length of time is not great.
Yeah, the technical term is no bueno.
No bueno. Yeah. When we look at these rack systems, some of these are 120-second time delays. The old school stuff, right? You're running a compressor for 2 minutes with no oil. You think that's okay? Probably not. So relying on the safety is a problem. When we're tripping on oil safety, we don't want that to reoccur. I don't want to mash that button and let me see if that happens again. I want to solve the problem. So that's the safety idea. Now the slug coming back is when I bring back a large amount of liquid, it's in my suction line. What I can't have happen is I cannot let that oil make it into the head of that compressor. If it does, the valves are going to be the failure point, right? We may actually break a crank or a piston, and if we weren't talking about Copeland, I'd say that's very likely. Copeland's are pretty robust beasts, but they're not. They can't defy physics. They cannot compress a liquid. They will eventually probably break the disc. Break one of the suction reeds in the valve plate is most likely where that's going to fail, and it is such an extreme force that it could break a connecting rod. It could send the piston to the bottom of that crank. Either scenario is going to require, at the very least, service, right? And replacement is likely, unfortunately. So getting that slug of oil back is similar to getting refrigerant flooding.
Right.
It's the same result. I end up, if there's enough of it, I end up with liquid in the head, and that's catastrophic.
Yeah, we just did a podcast about flooding and slugging, and that's of course liquid refrigerant. But liquid oil, same thing, right? It's it's like all things in moderation, right? You want
that's right.
You want it in the right amount, not too much. I think a lot of us could learn that in a lot of areas in our lives. But the same is true with taking sips of oil, not gulps.
Right.
You don't want the gulps.
My windings won't boil off oil.
Right. Good point. Good point.
Just so we know, we need that oil to fall into the sump and not make it to the head.
Yeah. Absolutely. Okay, so when we're talking about this type of suction trap, the type we're talking about right now, where the purpose is sips of oil return back to the system, talk a little bit more about the location of these and then some of the common things that you see. And now, again, there's a lot of variation in terms of engineering. There are some rules of thumb. I actually don't even want to get into that too terribly much because it really does depend on the type of refrigerant and a lot of factors. But what are some of the common things that you see in terms of where you're gonna put these traps and some of the common practices to keep that velocity up?
Sure, you're right. So, once again, talking about the suction. So we're coming out of the evaporator on our suction pipe. We're almost now. This is assuming my evaporator is the pipe that's leaving my evaporator is got to go up at some point.
Right.
Right. If it's dropping down, no big deal. I don't need a trap there. But if that pipe is going up, and it almost always does, I need a trap immediately coming out of the evaporator at the bottom of that we call the riser, the pipe that goes up.
Right.
Where that pipe goes up, in fact, anytime I have a pipe that goes up more than the diameter of the refrigerant pipe, we call that a riser. It doesn't have to be at the evaporator. It can be in other places too. But traditionally, there is one at the evaporator, maybe more farther down. But I've got to have a trap at the bottom of that riser. That's where it needs to be. And what that's going to do is it's going to prevent in low velocity or when that circuit shuts off or defrost or cycles off on temperature, that riser is going to be full of oil. The oil will fall. And I want it to fall into my trap instead of falling into my evaporator.
Right.
If it falls into my evaporator is the trap. And now I'm no longer exchanging heat, right? So my evaporator is not making temp properly. I'm probably flooding because I'm not bringing heat to the expansion device like it should. So the expansion device is going to be oversized. And I'm going to lose, depending on the size of this evaporator, 6-7 gallons of oil, right? All at the same time, right? Because I don't have a trap. So I always have to have a trap immediately coming out of that evaporator, hitting the riser, at the riser. Then the next place I'll have one is if that riser is really tall. And, you talk about rules of thumb and refrigerant types and all that. I can tell you on a 20-foot run, you're going to have a trap in the middle, somewhere, right? Different rules for that, but there's probably going to be what we call mid-trap, just because that is such an extreme distance to try to move oil suspended in vapor that sometimes it doesn't make it all the way to the top. It's gonna make it 3/4 of the way up and then fall. Well, we catch it in that mid-trap and then it can try again, and it's only got to go half as far.
Right.
So that works out pretty well. Then when we get to the top of that riser, the suction line now is going to make some horizontal run. And in my mind, I'm picturing like the roof of a grocery store where that pipe is running now towards the rack house. But that could penetrate the roof, on that remote condenser setup I'm talking about. It penetrates the roof there and then makes its way, towards the condenser. In either event, at the top of that, I'm going to want an inverted trap for the exact opposite reason. I don't want the oil to drain into that riser. I just worked so hard to get all the oil up to the top. If I shut that off, I can't risk that oil draining back down that riser, right? So I'm just going to throw an inverted trap. It's an upside down U, if you want to think of it that way.
Right.
So that suction line, that horizontal run, can't drain back into the riser, right? And then if I go back up again, in the example I gave you with the condenser on the roof, that was mounted 4 feet up, right? My pipe was on the ground. I'm going to go up 4 feet. Guess what? That's another riser.
Right.
So I need a trap at the bottom of that riser, but it's only 4 feet, so I don't need one in the middle. Right. Yeah. So that's kind of where we're going to put them. That's on the suction side.
And in terms of pitching, the pitching is super important. Like you ruin everything if you have a trap. I mean, just because the trap's sitting there, but if it's pitched the wrong direction, that ruins the whole thing that you're trying to do there.
Right. So on any horizontal run we have, we need that piping to slope towards my compressor. That's the whole the whole gravity portion of this, right? Gravity's going to pull that oil. Well, let's let it work for us, right? So we're going to pitch that. And we're going to drain towards our rack, or we're going to drain towards our compressor all the time. If we set that pitch incorrectly, or I have to go back up and then come back down. If I go back up as much as the thickness of my pipe, I've got an inverted trap, right? If it's not that much, it's not that extreme, then I'm going to flow back to my inverted trap. That's what's going to happen, and that pipe will just get smaller and smaller. Until it'll act like a trap, until we actually clear it. And when we clear it, we're getting that gulp again. So, yeah, we got to consistently pitch to the rack.
Yeah. The guideline, again, I think you already mentioned it, but the guideline that Copeland has here is 1/2 inch of fall for every 10 feet of run out.
Yep.
It's just kind of a standard.
Yep.
And again, like
one
you
by
said,
20, right? Yeah,
inch by 20. Yeah.
yeah.
Basically, just to kind of restate what you said, you're pitching towards the compressor and or towards your traps. So whatever
Right.
P traps
That's
you
right.
have, you're pitching in that direction
That's right.
consistently. So that way, oil's in the smallest possible place that
Yep.
it can be until it makes it to that compressor.
That's correct.
Yeah.
Yeah. Yeah. And, and I'm sitting here talking about all these unintentional traps. They're all pretty good size, right? So let's talk about when we want a trap, what size trap do we want?
Right.
Right. I mean, because it's like, well, you got this 3-foot trap now on the roof. Isn't that what I want? Right. What's a sip versus a gulp, I guess, would be the question. And it's really the rule of thumb here. Once again, there are some variations to this, but the general idea is about 4 times the size of the diameter of the suction pipe is where I want the entirety of that trap to fit. If it goes much bigger than that, it will work as a trap just fine, but we're going to be moving more oil than we typically want to on each of those sips, become a little more gulpy.
Is it a problem if it's smaller than that, though?
Right. So, no, it can be smaller than that. Sure, you're going to have little tiny sips, itty bitty little, you're sipping hot coffee that was a little too hot, right? Will it function? Well, if I'm trying to get up a really tall riser, not as well, because it's not going to have as much mass, right? But that mid trap should catch it, and it should move its way right up to the top. So it will work, but it is a little less effective if it starts getting smaller than that.
Yeah, and also if you get too exotic, making up your own custom stuff, you're also likely to add a lot more resistance as well than design. So yeah, you generally want to stay away from that.
Pre-made traps, if you can get them, are the way to go.
Yeah.
They're bent to the ideal radius. They're everything's perfect. You can make your own, and that is a really common thing, especially in the supermarket world. But commercial guys on the roof, they've got a box of fittings. They don't have a trap. Can they get away with it? Yeah, follow that rule that I just laid out, and it'll work just fine. But if you can get a pre-made trap, get it.
Yeah, that's the way to go. Yeah, for sure. Talk a little bit about this is one thing we haven't talked about before. Talk a little bit about discharge trapping. Why would you ever trap a discharge line?
Yeah, right. That's a good one, and we really haven't discussed that too much. So the issue we tend to have that requires that is when we have a system that turns off. When most of our conversations have been supermarket, right? We don't shut the rack out, right? Not on purpose. But when we're talking about these remote condenser setups, like I just, that example I keep bringing up, I'm definitely shutting that thing off every time it hits temp.
Right.
It's shutting off. It's also shutting off when it's going into defrost because it doesn't have enough load to keep running.
Right.
So in that scenario, the danger that I can have is if my condenser is taller than my compressor, if it's height-wise, gravity-wise, right? If it's slightly higher to extremely higher, then what will happen when I shut off is all of the oil that has been circulating through my entire system is in my condenser too, right? It's going to drain into my compressor. Well, where's it going to come in? It's going to come into the head. Right? It's going to come right into that spot. I was telling you, we cannot have liquid. And if it seeps through those valves and goes into the compression, stroke, we're going to blow the compressor up. So we're going to trap on that setup just the same as we will with suction. We're going to add a trap so that when I turn off the system right before the compressor, I've got a place for that oil to collect instead of going into the compressor. That's the primary purpose of that. We don't see that in supermarkets much. And the reason we don't is because we've got an oil separator that's usually at the very bottom. Mm-hmm. So when we shut off everything, it is my trap, and it's designed to hold oil, right, and separate it. So that oil draining from the condenser all the way down to the oil separator works just fine. So rack systems don't typically have a lot of trapping going on there, but we might if it's an extreme example and we really had to do something to remote that condenser. I think of the old motor rooms. These are kind of out of fad these days, but back in the day, when you walked into a grocery store, you went to the rack house, it was a room. You opened the door and turned on the light, right? Well, where's the condenser? That thing's probably 30, 40 feet on the roof.
Yep.
Do you think we're trapping that? Yeah, we got to trap that. Yep. That's just too far to push that. Refrigerant suspended in vapor. Right. So we're going to want to trap that too.
Yeah, and one of the things that I wanted to mention for AC guys, you're often going to see specs that have to do with inverted traps near air handling units or coils, evaporator coils. And in most air conditioning cases, what they're showing you is actually about ensuring that you don't have liquid returning to the compressor, liquid refrigerant, which is a whole different animal. And so I'm wanting to make that distinction. It's not really what we're talking about here, but you are going to see that. And again, there are a lot of other strategies that can sort of mitigate that. You can have a pump down strategy. There's a lot of different ways you can mitigate that. But in cases where you're likely to have large amounts of liquid refrigerant collecting in the evaporator coil, condensing, and then dropping right down a suction line into the compressor, that's why you have that inverted trap strategy. It's kind of actually... It's not really the opposite, but it isn't really a riser strategy. So for what we're talking about, if you had large amounts of oil, that could actually cause your evaporator coil to turn into an oil trap to some degree. Not really. I mean, yeah, no, it actually would. Yeah, I'm just trying to think about. I'm thinking of an old spec from a manufacturer that I got into an argument years ago with a trainer about. But just make sure that you know what you're talking about here, because again, that's kind of a residential. In some cases, you'll see it in commercial, but generally a residential HVAC thing.
Yeah, right. Yeah, definitely can get a little confusing to a guy.
Even I'm imagining in my head right now.
You need a trap. You need an inverted trap. You need what do you want me to do?
Right. But again, like if you've ever seen these specs, you literally have they want it coming out of the evaporator coil and going straight up. Yep. Well, in that type of strategy, if from an oil standpoint, you're actually going to have oil. You're creating a trap sitting in there. So, but again, these are smaller evaporator coils, and
your evaporator in that setup is almost always over your condenser.
Right.
You're talking about an attic setup or a closet with the evaporator on top. Of the air handler. In that scenario, my oil is going to naturally drain to my compressor.
Right.
So will my liquid refrigerant if I'm turned off and I condense. Correct. Right. So that is and it is exactly the opposite. Everything we're discussing is I'm coming out of my evaporator, and at some point I need that suction line to go up, not down, right? If I come out of my evaporator and I drop straight down, I don't need a trap there. It's going to fall. The oil's going to fall the correct direction down, right? Now, unless it's dumping right into a condenser, chances are it's going to hit a pit or something like that, make a long horizontal run, and then come back up. Well, guess what? When it comes back up, I better have a trap there.
Right. The question comes up about capacity and load when you're talking about design. How should you design it in terms of capacity and load when you have systems where you could maybe be running multiple compressors, or maybe you have a compressor that's running lower capacity, or maybe you have much lower load under certain circumstances? How does that affect this in the design?
Right. Okay. So and we didn't really talk about sizing risers, but that kind of plays into this as well. So, let's think about this for a minute. What we're actually doing is we've got saturated, or we've got refrigerant vapor saturated with oil. And we're trying to move the liquid oil in that vapor with velocity, with that vapor's velocity. That's what's actually making the oil move, right? So when we're sizing our suction system load-wise and efficiency, we want that suction pipe to be pretty decent size, so it has a small amount of restriction, or we end up with what we call drop, right? A difference in suction pressure at my compressor and my evaporator. That costs me kilowatts to generate that suction, so I don't want to have to overcome a lot of drop, right? So I want that pipe to be pretty good sized, and there's once again, rule of thumb for flow rate and all that. Challenge is the optimum flow rate through that suction pipe that gives me the perfect efficiency is not fast enough to move my oil up. So when I go to my risers, I have to sacrifice a little efficiency. I've got to get my velocity up. Well, the way I'm going to do that is by making my suction riser slightly smaller. In most scenarios, once again, there's math involved. You can't just go off of that, but that's the general idea. I'm just going to shrink that suction line a little bit. And that's going to cause the same amount of refrigerant flowing through it. It's going to cause an increase in velocity. That river that hits a narrow, right? You get a rapid. Well, that's what I want. I want the rapid to help push that oil up. Well, that's all based on one load, right? This evaporator is fully loaded, this compressor is fully loaded, and this is all running. So what happens when I have multiple compressors or multiple evaporators, both, and circuits is what I'm talking about. I've got some circuits, and then one circuit goes into defrost. I lose 6 cases off of this rack, just shut off, for an hour, 45 minutes, whatever. What happened to that main pipe's velocity. Well, it's less.
Right.
So I may not have enough oil, enough velocity now for my to carry my oil all the way up. So what I might do in that scenario, and this is really common in loops, is where we tend to use this. When I say loops, I'm talking about I've got one big suction pipe coming out of my rack that feeds a bunch of different circuits. Each circuit has 6 cases on it. For you folks, not super familiar with supermarket. In that type of a piping scenario, which is becoming, it's very old school, but it's becoming common again because you can reduce so much piping,
right?
Less potential for a leak, all the other things, right? So as that's making a return, we really got to think about it. But what we tend to do there in that setup is instead of having taking that riser and just shrinking the suction a little bit and making it go up, what we do is we figure out what that area is, what that volume is, and we run 2 much smaller pipes instead, or one smaller and one slightly larger. But we accomplish the same velocity with 2 pipes is the concept. Then when I go into defrost and I shut off my circuit, we switch to the smaller pipe. This is our dual riser setup that I'm talking about. And I've got the appropriate size pipe for the appropriate size load again. And then when it comes out of defrost, we run both again, right?
Right.
That's kind of the concept there.
So you're having to basically take into account whatever your lowest possible velocity situation is.
Correct.
So whether in the case like you're mentioning where you lost a circuit, or in the case where potentially you have some sort of variable capacity compression, where you're all the way down at the lowest possible point of compression, that also reduces your overall velocity. And so there's some design considerations, whether it's double riser, also your riser size, kind of all gets baked into deciding what strategy you're going to use there.
That's right. And as for the service guy, right, if you're out there working on this, you don't have to do that math. Somebody's already done that math for you. All you have to do is not change that, right? So, if you're doing some work and you got a leak, you got some rotten pipe you got to replace, and you're thinking about, I'm going to do this, be sure you pay attention to that setup that you're getting ready to cut into, and put it back that way, right? If you're not changing refrigerant types or anything else in that. That's what I'm talking about. Repairing it is don't disturb that. Somebody's already done that math. You're good to go. Just copy it.
As long as it's there. I think there are times where, as a service tech, you go and you're like, this doesn't have, the riser size is the same size, or it doesn't have a double riser, and I think maybe it should. That's where you go back to the original plans and specs and say, was it actually installed? And that especially happens is, hey, this has only been in 6 months and now we're having a lot of issues or whatever.
I was about to say, if it's run for 20 years, you probably don't need to go back to the plans and try to figure out, why it stopped running, why it ran 19 and a half years. It wasn't installed improperly. But that said, if it hasn't made it through a full season, temperature-wise, right, summer, winter, all the way around, if it's newer than that, you might want to be looking at the plans and making sure that we followed everything that should have been followed when it was installed. Yeah,
you mentioned this before. One of the biggest skills for a technician is to have that mindset of one of these things is not like the others, or one of these things has changed. What's changed here? And even with certain oil problems, did somebody shorten this line for some reason? Maybe they cut out a piece and they just pulled it up and reconnected it, or maybe somebody hit it with a lift or something goofy like that. It's when something's changed that then you need to start really paying attention, especially on older buildings. But even in the case of older buildings or older systems, maybe there was a particular lineup that got changed, or maybe there was a retrofit or some sort of change in a refrigerant or oil or something like that. And those are also areas where you need to be paying close attention. Yeah, that's right. In today's world, we're working on more of those than new. It used to be there was a lot of new stuff, right? But these days, there's not a lot of folks building brand new locations from scratch. They're out there, but there's not a ton of them. Most of the work that we're doing is retrofitting, upgrading, change outs, adding some things to an existing, those type things. Far more common, right? And that becomes more challenging too, because you've got to assume that it was installed originally correctly, and now I'm modifying that. And if I'm modifying that in a way that affects the old part, right, because it wasn't installed properly, I do have to take a more holistic view at everything. But I am looking at it from the perspective of
what's changed, what would cause that to impact this old part, right?
Yep.
You know, what's I've got a velocity change on the whole system. Yeah, I've taken 30% of the load off because I've got high efficiency cases. Right. Well, yeah, now I may have a problem with my old oil separator because I'm not moving the same volume through it that I was, right?
Yeah. If Roman was here, he would get into VRF, VRV and give a whole speech about that. So we'll probably do that another time. But it's worth just stating that as technology kind of advances, similar to where in market refrigeration, you've talked about, you have your kind of primary and secondary, your passive and your active oil systems. In VRF, VRV, there's a lot of strategies for oil return that help mitigate a lot of this in terms of like just actually running liquid through and kind of flushing oil back to the system. So there are a lot of ways that this can be done. A lot of what we're talking about here are that kind of standard, old school, passive trapping strategies to ensure that you get oil back.
That's right. That's right. In the supermarket world, hot gas defrost tends to cure a lot of these problems. Like you just talked about, pushing some refrigerant back through there. But the reality is, if I pipe it all correctly, it doesn't matter what little tricks and whatever I've got built in there to help. It's going to return. The oil will return. There's no question that it's worked. It works. It's very well proven.
Yeah.
My challenges become when I change those velocities. If I've got an existing system and I'm changing my velocity, why would I be changing my velocities? Well, you keep talking about variable speed compressors. Well, that's what my rack is.
Right.
My rack changes the size of its compression constantly by staging. Well, in the middle of the winter, when I don't have a huge load, I'm going to have less velocity. That's when my traps are going to start failing if they're not set up correctly. That's when I'm going to amplify any problems in this piping. That's when it's going to show up because the velocity is less. In the middle of July, I'm running everything as hard as it can. I'm probably going to have a really bad trap. It's going to clear oil. I'm going to be pushing hard enough. I'm going to be pushing it 100%. So that's another thing just to be aware of is, do I have a seasonal problem? Do I only have oil problems when it's winter? That's piping, right? If it fixes itself when it gets warm outside, that's a piping problem, right?
Yeah, and you're gonna notice this. The colder temps that you are operating in. So if you're working on low temp, ultra low temp, whatever, the lower the temperatures get, the more oil gets tricky to get back if it makes it out into the system. The more you really try to keep it close to the compressor for obvious reasons. You tend to have lower velocities. Again, you have lower mass flow rates. And I mean, I'm saying this as though all things are the same. And obviously, this is all an engineering problem. But from a very obvious standpoint, when you have lower pressures, which you do have on the suction side,
right,
in low temp, you have lower refrigerant density at that point as well. So you do tend to have more challenges, and also your oils tend to get thicker. A little bit stickier.
Minus 25.
They don't want to come back as much, which is why when we work in the air conditioning world, we run into it sometimes, but we don't have as much of a challenge with it, and that's where people will say, with modern refrigerants, they'll be like, well, yeah, the 410A is miscible with the refrigerant, therefore you don't ever have to trap. Well, first off, that's not necessarily true, but in air conditioning, we very rarely have these problems that we have when you get into refrigeration, especially low temp refrigeration. The colder it gets, the more it matters. And like you said, when it goes off, then you also have another set of considerations that you got to think about versus in grocery stores where it's running all the time.
Yeah, absolutely.
So what about liquid? When we talk about liquid lines and all that, why do we not have to worry about any of this on our liquid lines?
Yeah, that's a great question. So our oil is in the liquid too, of course. Right. But it's not in a vapor. So the liquid it's going to be mixed much better. Mm-hmm. It's going to be running at a higher velocity. And it's not going to have anywhere to stop and collect.
Right.
The liquid behind it, the liquid refrigerant, it's just going to push it. Right. It's just going to push it right along. That's a good question.
Yeah, and that's where things like even in heat pumps. So if you think about, for those of you who have worked on straight cool systems your whole life, I'll use an example from air conditioning here. If you've worked on straight cool systems your whole life that never go into heat mode, you will often have some more likelihood of issues with oil logging in the evaporator coil. You will run into more of that. where it actually, and again, this is the longer the lines are, the more kind of exotic things get. Whereas when you run a heat pump in heat mode, you are kind of driving all of that oil that's been sitting there back into the compressor. And that's the strategy. I mean, when you talk about hot gas defrost, sort of solving some of those issues at times because it kind of just, runs it right back through. It's the same kind of thing. And so in the same way that liquid is more dense and kind of carries oil along with it, hot gas, because you have higher velocities, higher temperature, that also kind of drives it back.
That's right. And even in off-cycle defrost and that kind of setup, we typically close the suction and the liquid line. A lot of guys don't think about that, but we're intentionally trapping the refrigerant inside the evaporator, and then we're running heat across it. Well, it may not be electric heat, may not be hot gas. The fan's running though, and it's bringing load that I don't have refrigerant to cool. So that's going to cause that pressure to increase inside that evaporator to higher than suction, right? And when I come out of defrost, I'm going to clear all my traps. It's going to just push right out of there at that higher velocity. Even though it's vapor, it's going to bring my oil back. That's when that's going to happen, through natural design. I'm going to clear my traps after defrost.
Yep. So for people who are interested in learning more about general topics related to all this stuff we're talking about, not necessarily this, but there's going to be a lot of different things. Copeland both has in-person instructor-led courses that I would encourage you to look at, as well as they have put up a bunch of online courses that are free for you to access. HVACRschool.com/Copeland-course is going to take you to a basic refrigerant kind of refrigeration course, give you a chance to go through that. It's a good one for contractors out there if you want to, give something to your technicians to have them get a certificate and kind of follow up, make sure they know the basics. But there's a lot of other options, all the way from basics, intermediate, advanced, with Copeland, and I would encourage you to check out what they have. Again, go to that link, hvacrschool.com/Copeland-course, to find out more, and you can also see all the other courses there with them. And also, just as another side note, we have a whole series of videos that I did with Matthew. Or I didn't do them with Matthew. We produced them for Matthew. He did all the classes over at HVAC School. So if you look at, there's a, what is the name of the series? Is it grocery refrigeration, market refrigeration?
The refrigeration cycle.
Okay.
And there's like 13 parts, right? We broke it down.
Yep.
Each part will have a title of the subject matter, the main subject matter we're going to talk about. They're about an hour or so. So if you forgot what an EPR is, I've got an hour on that. Jump in there and we'll fill you in.
Yeah, and it comes from a very grocery refrigeration perspective. But what I've heard from a lot of technicians out there is that it really applies to a lot of other things. Sometimes there's problems that are a big problem in grocery refrigeration that might not be so big of a problem in air conditioning, but understanding it in the grocery refrigeration side can bring you some perspective. And also, who knows, maybe someday you'll want to do some of this crazy
join us.
Yeah, grocery refrigeration.
Come to the dark side.
Yeah,
right.
Stuff. So who knows? But I think that's it. I think that's it for today. Thank you, Matthew, for taking the time.
Yeah, it was great being here.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.